Hello, and welcome to the Sleep Scientist channel. Tonight, we drift into one of the deepest mysteries of the universe as we gently explore how black holes bend space and time. In this quiet journey, travel to the shadowed edges of gravity's strongest realms, where light curves, time stretches, and the fabric of reality bends softly around these silent giants. Let your thoughts slow, let your breathing settle, and allow the calm, steady pull of the cosmos to guide your mind toward deep, peaceful rest as we unravel the tranquil science behind black holes and their extraordinary influence on spacetime itself. The universe is a quiet ocean of spacetime, stretching endlessly in every direction. Within this ocean, gravity shapes the currents, bending the fabric of reality in ways both subtle and profound. And at the heart of this cosmic ballet lies one of the most mysterious creations of nature, the black hole. A black hole is not a hole in the traditional sense, nor is it a void waiting to be filled. It is the collapsed core of a massive star, compressed into a point of unimaginable density. In this tiny region, known as a singularity, the laws of physics, as we know them, begin to unravel. But this unraveling is not violent for the distant observer. It is quiet, silent, patient, a gentle but unstoppable distortion in the fabric of space-time. To understand how black holes bend space and time, we must first understand that space itself is not empty. It is a flexible, stretchable, responsive fabric described by Einstein's theory of general relativity. In this view, gravity is not a force, but a curvature. A mass warps the surrounding space-time, and other objects follow the curves it creates. The larger the mass, the deeper the curve, and nothing creates a deeper curve than a black hole. Imagine placing a heavy iron sphere on a vast rubber sheet. The sphere makes a dip, and anything placed nearby slides toward it. Now, imagine replacing the iron sphere with something infinitely heavy. The sheet would stretch downward without limit. That infinite well is the closest analogy we have to a black hole's gravitational pull. Yet, black holes do not drag you in suddenly. There is no snapping, no violent tug from afar. Instead, the curvature grows stronger slowly, steadily, predictably, as you approach. From far away, you could orbit a black hole as safely as orbiting any star. It is only near the boundary, the event horizon, where the distortion becomes extreme. The event horizon is not a surface, but a point of no return. It is the threshold where gravity becomes so strong that not even light can escape. Once crossed, the path inward is unavoidable. However, someone falling in would not notice crossing the horizon. No flash, no warning, just a calm continuation of their descent into deeper curvature. Time behaves strangely near this boundary. For a distant observer, time for the falling person slows dramatically. Minutes stretch into hours. Hours stretch into infinity. The falling person appears frozen in place, suspended on the edge of the event horizon forever. But, from their perspective, their journey continues naturally, smoothly, without delay. This difference arises because black holes do not only bend space, they bend time itself. Time slows in strong gravitational fields, a phenomenon known as gravitational time dilation. near a black hole, this effect becomes extreme. Imagine two clocks, one far from the black hole and one close to it. The distant clock ticks at a normal rhythm. The clock near the black hole ticks more slowly, almost imperceptibly. At the event horizon, the clock appears to nearly stop entirely, at least to the outside observer. This slowing is not an illusion. It is the nature of time interacting with intense gravity. But how does this look? Imagine floating near a black hole and watching the universe beyond. Galaxies would seem to speed up. Stars would shift in brightness and movement. The cosmos would age before your eyes. You, near the black hole, would experience minutes, while the universe experiences millennia. The black hole shapes not only time, but also the path of light. Light passing close to a black hole curves dramatically. This bending of light creates a glowing halo known as the photon ring. It is a perfect circle of distorted light, an echo of the universe around the black hole. The images captured by the Event Horizon Telescope, showing the fiery ring around M87, revealed this effect for the first time. Photons caught in the gravitational grip orbit the black hole 1, 2, 3, or even many more times before escaping. These delayed, looping photons create layered rings of light, each representing a different path through warped spacetime. It is like looking at a hall of mirrors built by gravity itself. Inside the event horizon, the curvature becomes so intense that all possible paths lead inward. It is not the black hole pulling you down. It is space-time guiding your path, tilting every direction into the center. Space becomes time, and time becomes space. Movement inward becomes as inevitable as moving forward in time. At the singularity, the curvature becomes infinite. Physics breaks down. Equations fail. Space and time lose meaning. While the singularity is predicted by current models, many scientists believe that a future theory of quantum gravity will reveal its true nature. Perhaps it is not a point, but a region of extreme quantum structure. Perhaps it is something more exotic. We do not yet know. But the journey toward understanding black holes continues. And the more we learn, the more we see that black holes are not monsters, but essential parts of the cosmos. They regulate galaxy growth. They shape stars. They recycle matter through jets and winds. They influence the evolution of everything around them. Their presence is not destruction, but transformation. A quiet, cosmic reshaping. A bending of space and time that reveals the deeper architecture of the universe. To understand how black holes reshape reality, we must look more closely at the fabric of space-time itself. Space-time is not a background or a stage. It is an active participant in the evolution of the universe. It curves. It flows. It ripples like water disturbed by a stone. And black holes are the deepest stones ever cast into that cosmic ocean. Imagine space-time as a calm lake under a dark, star-filled sky. When a massive object, like a star, floats upon its surface, it makes a depression. This depression is gravity. It guides planets, comets, and light itself into curved paths. But a black hole is a weight so immense that the lake's surface plunges into a well without bottom. This well is not a place you fall into. It is a direction in space-time that points toward the singularity. The deeper the well, the more dramatically it bends the paths of objects and light around it. Photons skim along its rim like fireflies caught in swirling wind. Planets could orbit it as they orbit normal stars, though they would see the sky twisted in impossible ways. If you orbited a black hole, you would see your own path reflected in rays of light that curved around it, returning to your eyes. It would be like watching the universe through a warped glass bowl. The bending of spacetime also affects how objects move through time. Time passes differently at different depths of the gravitational well. This is why astronauts on the International Space Station age slightly slower than people on Earth. They are farther from Earth's center of gravity, experiencing slightly less curvature. The effect is tiny near Earth, but near a black hole, the effect becomes astonishing. A person hovering safely outside a black hole's event horizon might experience an hour while centuries pass outside. If they later returned home, they would discover that the world had aged far beyond them. Loved ones would be gone. Civilizations might have risen and fallen. Yet for the traveler, only a short time would have passed. This is not fiction. It is the natural consequence of Einstein's equations. Space-time bends. Time slows. Black holes magnify these effects to their extreme. They turn the universe into a place where time itself becomes elastic. Nothing shows this more clearly than the phenomenon of spaghettification. Despite its whimsical name, it describes the very real stretching effect caused by tidal forces near a black hole. If you fell feet first toward a black hole, the gravitational pull on your feet would be stronger than the pull on your head. The difference grows rapidly as you approach the horizon. Your body would stretch along the direction of gravity while being compressed sideways. This stretching would be gentle at first, barely noticeable, a soft, tugging sensation. But closer to the horizon, it becomes extreme. Eventually, it becomes fatal. However, the severity depends on the size of the black hole. Small black holes have intense tidal forces at their horizons. Large black holes, especially supermassive ones, have gentle horizons where tidal forces are weak. If you fell into a supermassive black hole, you might cross the horizon without feeling anything at all. Silent, peaceful, weightless. Only deep inside would the tidal forces become overwhelming. These inner regions remain one of the greatest mysteries of modern physics. General relativity predicts the singularity. Quantum mechanics suggests that something else must exist, perhaps a quantum core, perhaps a structure made of fundamental spacetime units. Some scientists speculate that information falling into a black hole may be encoded on its surface in a holographic pattern. Others propose that black holes are gateways to other regions of spacetime, though no evidence supports this yet. What we do know is that our current theories cannot describe the environment inside the singularity. It is a frontier we cannot yet cross. The story becomes even more fascinating when we consider rotating black holes. Most black holes spin because the stars that create them spin as well. A spinning black hole drags spacetime around with it. This swirling effect is called frame dragging. Imagine placing a spoon in honey and twisting it. The honey twists around the spoon. Similarly, spacetime twists around a rotating black hole. This rotation creates new structures. Instead of a single event horizon, a rotating black hole has two: an outer horizon and an inner horizon. Between them lies a region where space-time is dragged so forcefully that nothing can remain still. All objects are compelled to rotate with the black hole. Even light cannot resist this twist. This region is known as the ergosphere. Here, strange things become possible. A particle entering the ergosphere can split, with one part falling into the black hole and the other escaping with more energy than it entered with. This process is known as the Penrose process. It suggests that energy can be extracted from a rotating black hole. It is as though the black hole's spin is a reservoir waiting to be tapped. Though we cannot yet harness such energy, nature may already do so. Jets shooting from the poles of supermassive black holes may derive some of their power from this rotational extraction. These jets span thousands of light years. They heat surrounding gas. They shape the formation of galaxies. They regulate the birth of stars. Black holes, far from being destroyers, are architects of cosmic structure. Their gravitational influence sculpts the cosmos on every scale. Stars cluster around them. Galaxies form disks and spirals shaped by their central mass. Even the dark matter halos surrounding galaxies may respond subtly to black hole activity. It is a cosmic dance choreographed by gravity. And at the core of this dance lies the bending of space-time. The curves, the warps, the slow ripples that pass through the universe like silent waves. These ripples, gravitational waves, were first detected in 2015. Two black holes collided, merging into one. The event released more energy than all the stars in the universe shining at once. But the energy did not shine. It rippled. It shook the fabric of space-time. These waves stretch and compress reality as they pass. They move through everything, through stars, through planets, through your body. Yet, the effect is so faint that only the most sensitive detectors on Earth can measure them. This discovery opened a new window into the universe. We can now listen to the echoes of black holes merging. Each signal is a whisper from billions of years ago, a soft tremor carried across the cosmos, a message from the deep curvature of space-time. Black holes, once thought to be cosmic monsters, are now storytellers. They reveal the inner workings of gravity. They show us how space bends, how time stretches, how the universe behaves under its most extreme conditions. Their silence speaks volumes. Their shadows reveal light. Their depths reshape time. They are mysteries, yet they bring clarity. They are destroyers, yet they create cosmic order. They are voids, yet they illuminate the nature of space-time. To grasp how black holes influence the universe around them, we must examine the strange and beautiful environment that forms just outside the event horizon. This region, known as the accretion zone, is one of the most energetic places in the cosmos. And yet, despite its violence, it holds clues to the quiet, smooth curvature of space-time beneath it. Matter drawn toward a black hole rarely falls straight in. Instead, it spirals gently, forming a glowing disk of gas and dust. This disk heats to extraordinary temperatures as friction and compression build. Electrons whirl, atoms collide, light escapes in brilliant arcs. All of this unfolds in a smooth, swirling ballet, guided by gravity's invisible curves. For a distant observer, the disk appears bright and distorted. One side glows more intensely than the other. This difference is caused by relativistic beaming. As matter on one side spins toward us, its light is boosted. As the other side spins away, its light softens. The result is an asymmetric glow that circles the black hole like a cosmic lantern. The disk also reveals how light bends in extreme gravity. Some photons travel directly from the disk to the observer. Others loop around the back of the black hole, curving along its warped spacetime before reaching the observer's eyes. This creates multiple images of the same region, stacked like reflections in a funhouse mirror. These echoes of light softly outline the shadow at the core. This shadow, famously captured by the Event Horizon Telescope, is not the black hole itself. It is the silhouette of the event horizon, the place where light disappears into the curvature of spacetime. The bright ring around the shadow is formed by photons on the edge of escape, dancing along their final orbits. It is a portrait painted by gravity, a whisper of the black hole's presence, a glimpse into the shape of warped spacetime. If you could float safely near this region, you would witness one of the most breathtaking sights imaginable. The sky would curve unnaturally. Stars behind you would appear ahead. Constellations would twist and shimmer like reflections on dark water. Light from the accretion disk would smear into streaks as gravitational lensing bent its path around the black hole. The universe itself would feel rearranged, not chaotic, just curved, softly, inevitably. But as astonishing as the outer regions are, the true strangeness of black holes lies in the structure of spacetime beneath the horizon. According to general relativity, once inside, all directions lead inward. Space becomes time. Time becomes space. Your forward motion becomes movement toward the singularity, no matter how you try to resist. This transition is not violent. It is smooth, unstoppable, like drifting down a river whose current gradually strengthens. Some theories propose that the interior of a black hole contains layers, each governed by different gravitational intensities. The inner horizon of a rotating black hole introduces even more complexity. Here, the flow of spacetime may reverse. Energy fields may amplify. Particles may experience infinite boosts. This region, known as the Cauchy horizon, challenges our understanding of cause and effect. It stretches the very idea of time to its limit. Because of these complexities, many physicists believe nature protects itself from paradox by preventing stable inner horizons. Incoming light and energy may accumulate there. This buildup could destabilize the region, smoothing out strange behaviors before paradoxes emerge. The interior might be chaotic, or gentle, or something beyond our mathematics. We simply do not know. What we do know is that the boundary between the known and the unknown hides behind the event horizon. And yet, black holes communicate with the outside universe in surprising ways. They vibrate, they hum, they ring like cosmic bells when disturbed. These vibrations release as gravitational waves. Picture two black holes spiraling around each other. They orbit faster and faster as they draw closer. Their immense gravity stretches spacetime like a rubber sheet pulled tight. When they finally collide, spacetime snaps into a new configuration. This snap releases waves that move outward across the universe. These waves carry information about the mass, spin, and structure of the black holes involved. When these waves pass through Earth, they alter distances, compressing and stretching space by tiny amounts. The effect is so subtle that only the most precise instruments can detect it. And yet, this whisper from billions of years ago tells us a story. It tells us how space-time behaved under the most extreme conditions. It tells us that black holes truly exist. It tells us that gravity is not just a force, but a shape. The existence of gravitational waves completes Einstein's vision. He predicted them more than a century ago, describing them as ripples in reality. Today, we can listen to those ripples. Each detection is a cosmic heartbeat, a signature etched by black holes as they reshape the universe. They are messages encoded in space-time, messages of motion, messages of curvature, messages of the deep structure of reality. Yet, perhaps the most profound effect of black holes is on the flow of time itself. To understand this, imagine placing 3 clocks at different distances from a black hole. The farthest clock ticks normally. The second, placed closer, ticks more slowly. The third, positioned just above the event horizon, ticks so slowly that its seconds stretch into centuries. All 3 clocks are correct. Time is not universal. It changes with gravity. It changes with motion. It changes near black holes more than anywhere else. If you dropped toward a black hole, you would notice nothing unusual at first. But an outside observer would see you slow, then freeze, then fade. To them, you would never quite cross the horizon. Your final moments would hang forever on the edge of time. This difference between perspectives reveals a truth about the universe. Reality is not a single experience. It is many, woven together by space-time. The black hole does not distort your passage. It distorts the way that passage is seen. It bends the stories that observers can tell. Black holes bend space. They bend time. They bend light. They bend stories. And through these bends, they reveal the deeper mechanics of the cosmos. Not through violence, but through geometry. A geometry written in curves rather than lines. A geometry of gravity. A geometry of existence. As we journey deeper into the strange physics shaped by black holes, a new idea emerges, one that challenges our intuition about the boundaries of reality. This idea is known as the information paradox. It begins with a simple question, a question that has puzzled scientists for decades, a question whispered at the edges of space-time. What happens to information that falls into a black hole? In everyday life, information cannot be destroyed. If you burn a book, the words are scrambled, not erased. If you break a glass, its atoms still contain the story of what once was. Physics protects information. It guards it. It preserves it across time. But a black hole seems to violate this rule. When matter falls beyond the event horizon, it disappears. Its structure dissolves. Its identity vanishes. The black hole reveals nothing about what it has consumed. It only shows three features: mass, spin, and electric charge. This simplicity is known as the no-hair theorem. A black hole has no other distinguishing features. It has no memory of what formed it. It has no record of what fell inside. At least, none that we can see. For decades, physicists struggled with this contradiction. If information truly vanished, it would break quantum mechanics. If information somehow remained, it would require new laws of physics. The universe seemed to be guarding a secret wrapped inside the horizon, a secret that refused to be revealed. Then came Stephen Hawking's surprising discovery. He realized that black holes are not completely black. They emit a faint glow. This glow is called Hawking radiation. It arises from quantum processes near the horizon, and it causes black holes to slowly evaporate. This revelation created an even deeper mystery. If a black hole evaporates completely, what happens to the information inside it? Does it vanish along with the black hole? Does it leak out in the radiation? Does it remain encoded in space-time itself? The answers remain uncertain. But the paradox forced physics to evolve. Some theories suggest that the surface of the event horizon stores information like a hologram. Every photon, every atom, every detail of everything that has ever fallen in. This idea forms the heart of the holographic principle. According to this principle, the three-dimensional universe may behave like a projection of information encoded on a distant surface. A cosmic hologram. A universe written on the boundary of space. If true, black holes are not destroyers of information, but guardians of it. They store it in delicate patterns on their surface. They preserve it through quantum entanglement, and they release it slowly as they radiate away. This release would be subtle, slow, nearly impossible to detect, yet still consistent with the rules of physics. Other theories propose that information becomes woven into the structure of space-time itself, stretched across dimensions we cannot see, pinned to geometric fibers deep beneath the horizon, hidden but never erased, waiting for a more complete theory of quantum gravity to reveal its pattern. Some physicists suggest that a black hole may be more like a doorway, a bridge to another region of space-time, a wormhole formed by the intense curvature of gravity. If so, information would not be lost. It would simply continue elsewhere, beyond our view, beyond our reach, but still intact. These ideas are speculative. They live on the boundary between mathematics and imagination. And yet, each one attempts to protect the same principle. The universe does not destroy information. It merely hides it, transforms it, shifts it into new shapes, much like space-time itself. Still, the paradox remains unresolved. It sits like a quiet puzzle at the heart of theoretical physics, a gentle reminder that even the sharpest minds have not fully grasped the nature of gravitation, that the smooth geometry of space-time still holds mysteries, that black holes are more complex than their elegant equations suggest. This uncertainty invites us to see black holes not as cosmic endings, but as beginnings, as laboratories for new physics, as teachers of geometry, as portals to deeper understanding. They challenge our concepts of space. They challenge our concepts of time. And most intriguingly, they challenge our assumptions about reality itself. While the mathematics continues to evolve, one truth remains clear. Black holes reveal the intricate relationship between gravity and quantum mechanics. They expose the boundary where our theories break, where known laws dissolve into questions, where curiosity replaces certainty. And yet, despite their complexity, black holes are peaceful in their purpose. They bend spacetime not through chaos, but through order. They follow the geometry of mass. They shape the universe through simple curves drawn across vast distances. They pull matter inward. They stretch time outward. They write the story of the cosmos in gravitational lines. As we reflect on these paradoxes, a deeper feeling emerges, a quiet awe at the harmony of the universe, a sense that even its strangest regions maintain a delicate balance, a balance between destruction and preservation, between simplicity and complexity, between darkness and understanding. The black hole does not offer easy answers. It offers depth. It offers wonder. It offers a gentle challenge to our imagination, a soft tug pulling us toward the horizon of knowledge, a horizon we, too, must approach slowly, patiently, curiously. As we drift deeper into the fabric of this cosmic story, a new question begins to take shape. Not a loud question, not a sharp one, but a soft, lingering curiosity that echoes gently across the curvature of space-time. What does it truly feel like to approach a black hole? What would an observer see? What would they experience? How would their sense of time begin to shift as gravity tightens its grip around them? These questions guide scientists toward one of the most fascinating and surreal predictions in physics: gravitational time dilation. A phenomenon that bends not just space, but the very rhythm of time itself. Einstein predicted that the stronger the gravitational field, the slower time will flow. Near a massive object, clocks tick more slowly. Moments stretch. Seconds loosen. Time itself becomes elastic. Near a black hole, this effect becomes extreme. Imagine drifting toward the event horizon. You remain calm, quiet, protected inside a sturdy spacecraft. You feel no sudden change, no jolt, no pull. Gravity does not yank you. Instead, it eases into your experience gradually, smoothly, almost silently. But to a distant observer, someone watching you from far away, the story looks very different. They would see your movement slow. They would see your signals stretch into lower and lower frequencies. Your motion softens. Your time dilates. Your body appears to fade into a slow-motion whisper of light. As you approach the horizon, you seem to freeze, suspended, motionless, as though time around you has stopped entirely. From their perspective, you never cross the horizon at all. But from your perspective, inside your own timeline, everything continues normally. Your heartbeat remains steady. Your thoughts unfold naturally. The horizon approaches quietly, gracefully. This difference reveals one of the most mesmerizing aspects of general relativity. Time is not universal. It is personal. It flows according to gravity. And black holes create the most dramatic tidal differences in the universe. Deep inside this region, something strange happens to space itself. The radial direction, once outward and free, begins to tilt inward. It becomes trapped. To move forward in time is also to fall inward. Space-time guides everything toward the singularity, not with force, but with geometry, an unavoidable curve. This leads to another haunting idea. Inside the event horizon, all possible paths lead to the center. Even if you try to escape, even if you fire rockets, even if you turn around, every direction becomes inward. Space folds in such a way that your destination is no longer a place you choose. It is a place geometry chooses for you. But again, this happens without violence, without drama. The fall feels natural, smooth, like drifting along the current of a deep river, a current made of space-time, a current shaped by gravity. Now, imagine approaching a rotating black hole. These black holes spin rapidly, twisting space-time around them. This phenomenon is called frame dragging. As you fall, you are gently pulled into the direction of the spin. Space itself rotates. Time swirls. You become part of a cosmic whirlpool, a gravitational eddy turning in quiet circles. Inside this rotating structure lies the ergosphere, a region where space-time is dragged faster than light could escape. Not because light slows down, but because space itself moves beneath it. In this region, even standing still would require moving faster than the speed of light, which is impossible. So everything inside must swirl with the rotation of the black hole. Matter, energy, light, even time. This rotation opens the door to another remarkable possibility: energy extraction. Under certain conditions, objects entering the ergosphere can come out with more energy than they had when they arrived. This process, known as the Penrose process, reveals that black holes are not always simple sinks. They can also behave like cosmic turbines, transforming rotational energy into escaping radiation, feeding the universe instead of only consuming it. These predictions, though deeply mathematical, paint a picture that is almost dreamlike, a picture where space flows like water, where time stretches like soft fabric, where geometry becomes alive, elastic, and fluid. Black holes are not static monsters. They are dynamic sculptors of reality, designers of curvature, architects of time, and still, for all their complexity, they remain silent. No sound escapes them. No light returns from their depths. They shape the universe quietly, patiently, with gravity as gentle as it is powerful. As we float in this conceptual space, a feeling of calm begins to settle in, a sense of cosmic serenity. The universe, even in its most extreme forms, moves with elegance, with balance, with a slow, deep motion that resembles the rhythm of breathing. Black holes do not break the universe. They reveal its rules. They show us what gravity can do, what time can become, what space can feel like when stretched to its limits. They are windows into the hidden architecture of existence, a quiet reminder that the cosmos is stranger, softer, and more beautiful than we often imagine. As we continue drifting through the quiet geometry of black holes, another question begins to rise softly in the background. A question shaped not by fear or urgency, but by gentle curiosity. What happens to light as it tries to move near a black hole? Light, after all, has no mass. It weighs nothing, floats effortlessly through the universe. It should not be influenced by gravity at all. And yet, it is. Not because gravity pulls on light, but because gravity bends the space through which light travels. To understand this, imagine light as a traveler walking across perfectly flat ground. On flat space, its path is straight, simple, clean. But near a black hole, the ground curves, dips, stretches. The traveler is not pushed. It simply follows the shape of the ground. Its path bends naturally, gently, beautifully. This bending of light is called gravitational lensing. It turns black holes, these dark, silent spheres, into powerful cosmic magnifying glasses. When light from distant stars passes near them, its path curves. It arcs around the black hole, sometimes splitting into multiple paths, sometimes stretching into arcs or rings, sometimes bending so dramatically that we see one star appear in several places at once. This creates one of the most hauntingly beautiful structures in astrophysics, the Einstein ring, a perfect, glowing circle of light formed when a distant star aligns just right behind a massive object. The black hole becomes a lens. The universe becomes artwork. Light becomes a gentle curve around darkness. But near the event horizon, this bending grows so intense that photons can enter stable orbits. This region is called the photon sphere, a shimmering, invisible ring where light circles endlessly. Round and round it goes, not falling in, not escaping, just orbiting, trapped on the edge of gravity's final boundary. A ballet of photons dancing along the curve of spacetime. This creates the glowing outline we often see in black hole illustrations. Not the black hole itself, but light from the surrounding region bent into a halo of fire. This glowing ring is not imaginary. It was photographed, captured by the Event Horizon Telescope in 2019. Humanity's first direct image of a black hole, a soft, blurry circle of light embracing a dark center. A cosmic portrait, billions of years in the making. This moment changed more than science. It changed our imagination. For the first time, we saw, not guessed, not simulated, but saw how space-time curves around a black hole. How light bends, how darkness shapes the world around it. Yet, the bending of light is only one part of the story. Gravity also bends time. We can think of time as a river. In most of the universe, the river flows quickly, smoothly, at a steady pace. But near a black hole, the river slows. Its current weakens. Its flow softens. Seconds stretch. Minutes loosen. Hours drift apart. Imagine two clocks. One far from the black hole. One slowly approaching the horizon. The distant clock ticks normally, steady, predictable, but the falling clock ticks more slowly. Its rhythm lengthens. Time becomes syrupy, heavy, almost sleepy. If you watched the falling clock from afar, it would seem to slow down. Tick, tick, pause, longer, slower, as it approaches the horizon. The pauses become infinite. The clock appears frozen, suspended at the edge of time. But from the perspective of the falling clock inside its own frame of reality, it ticks at the normal pace. Its seconds feel like regular seconds. Nothing feels strange. Nothing feels stretched. Its journey continues without interruption. This difference is the heart of relativity. Time is not absolute. It changes with gravity. It adapts. It bends. It breathes. And black holes bend time more than anything else in the universe. Even more remarkable is what happens to light emitted from near the horizon. As it climbs out of the deep gravitational well, its wavelength stretches. It becomes redder, longer, softer. This is called gravitational redshift. It transforms light into whispers, photons into fading sighs, signals into gentle, dying echoes that fade into darkness before ever reaching us. This is why, from the outside, nothing seems to cross the event horizon. Light cannot report the crossing. Time cannot communicate it. Information becomes trapped in silence. All of this reveals a profound truth. Black holes do not simply devour. They erase the difference between space and time. They unite them into a single curved structure. A structure where light bends like a soft ribbon, where time stretches like warm honey, where the universe behaves as though it is dreaming. And still, despite all this strangeness, the physics remains smooth, elegant, consistent, even gentle in its own way. Black holes are extreme, yes, but they are not chaotic. They are precise, predictable, structured by the most fundamental geometry of the cosmos. As we drift away from the photon sphere and the glowing rings of bent light, the universe seems to quiet down again. The stars return to their places. The darkness softens, and the calm, steady hum of space-time accompanies us forward, leading us deeper into this journey of understanding. As we continue our slow drift through the curved depths of relativity, another quiet mystery begins to surface. A mystery about information. Not physical matter, not energy, but the very patterns that describe reality. What happens to information when it falls into a black hole? This question sits at the crossroads of physics. It is gentle in form, but immense in consequence. Because in the universe, we know, information cannot simply disappear. It can change shape. It can hide. It can scatter. But it cannot be destroyed. And yet, black holes seem to swallow everything without a trace. Matter falls in. Light falls in. Patterns fall in. All crossing the event horizon in complete silence. From the outside, nothing returns. Not shape. Not structure. Not memory. Just darkness. This leads to one of the most famous puzzles in modern science, the black hole information paradox. A paradox that whispers to physicists in the quiet hours of the night. A paradox that challenges the basic laws of nature. On one side is general relativity. Smooth, continuous, geometric. It paints the black hole as a simple endpoint. everything falls in. Nothing escapes. On the other side is quantum mechanics. Granular, precise, structured. It insists that information must be preserved. No exceptions. Two worlds, two rules, one conflict. This tension creates a soft but powerful question. Does the black hole truly erase information, or does the universe find a subtle way to preserve it? One idea suggests that information becomes encoded on the event horizon, spread thinly across its surface, not inside the black hole, but on the boundary around it. A cosmic memory layer, a holographic imprint, a surface carrying the story of everything that falls in. This idea leads to the holographic principle, the notion that all the information inside a region of space can be stored on its boundary. A universe that behaves like a vast, quiet hologram. Depth encoded on surfaces. Complexity encoded on simplicity. But there is another possibility. Hawking radiation. The slow, soft glow that black holes release over unimaginable timescales. A whisper of energy emerging from the edges of spacetime. A gentle evaporation. Perhaps this radiation carries away information. Not quickly, not clearly, but subtly, encoded in faint, quantum patterns. A cosmic leak restoring the balance. If this is true, black holes are not final tombs. They are temporary states, long-lived but finite, slowly returning every bit of their history back to the universe. Not in shouts, not in bursts, but in a faint, quiet exhale of radiation. This possibility softens the paradox, not solving it entirely, but guiding us toward a gentler understanding. A black hole may bend space. It may stretch time, but perhaps it does not break the rules of information. It simply rewrites them in a form too subtle for us to notice. Another idea proposes that the inside of a black hole is not what we imagine, not a singular point, not a place where physics collapses, but a region structured by new forms of quantum gravity, smooth at scales we cannot yet measure, continuous in ways our current equations cannot yet describe. In this picture, the singularity dissolves, not violently, but gracefully, replaced by a dense, curved region where space-time does not end, it transforms, becomes something new, something smaller, something softer, something hidden. These ideas point to a deeper truth about black holes. Their mystery is not meant to confuse us. It is meant to guide us. They sit at the intersection of our theories, where the smooth geometry of relativity meets the sharp structure of quantum physics, where time stretches, where light bends, where information flows in ways we do not yet understand. Black holes are not obstacles. They are invitations, inviting us to see the universe differently, inviting us to imagine deeper layers beneath the surface of reality, inviting us to slow our thoughts, to listen to the quiet curves of space-time, to follow the soft pull of gravity toward understanding. As we drift further into this story, the universe feels larger, more mysterious, more interconnected. Every question opens another. Every answer folds into a deeper truth. And through it all, the cosmos remains calm, vast, patient, unfolding slowly, like a long exhale in the dark. Black holes bend space. They bend time, and perhaps, in their own silent way, they bend our imagination too gently, reshaping how we understand reality itself. As we float in this quiet current of cosmic thought, another subtle phenomenon comes into view. It is the warping of space and time, not just near a black hole, but far beyond it. The presence of a black hole stretches space-time like a weight on a rubber sheet. Stars orbit in gentle curves. Light bends into arcs. Galaxies sway ever so slightly. The influence extends across thousands of light years. It is a slow, subtle choreography, an invisible hand guiding the dance of matter and energy. Every star, every planet, every photon adjusts its path. Not abruptly, not violently, but gracefully, as though responding to an unseen conductor. Even the shape of entire galaxies can be affected. Spirals form, disks rotate, jets emerge from active centers. Supermassive black holes shape the environment around them. They regulate star formation. They sculpt clouds of gas. They heat interstellar matter with their quiet, relentless pull. This cosmic influence reveals a delicate paradox. Black holes are invisible, almost silent, yet they exert enormous power. They shape the visible universe through invisible forces. Their effects ripple outward, sometimes imperceptibly, yet always present. Now consider time near these gravitational giants. It moves differently depending on proximity. Closer to the horizon, it slows. Farther away, it flows normally. The difference can span millions of years when observed from great distances. A single journey near a supermassive black hole could alter how you experience time relative to the rest of the universe. This is not abstract theory. We observe these effects in binary systems, where a black hole orbits a companion star. X-ray emissions reveal matter spiraling inward. Light curves show time dilation. Gravitational waves ripple outward, carrying signatures of curved space-time. The more we study these phenomena, the more we realize that black holes are central to cosmic evolution. They are not merely destructive. They create order. They shape structure. They influence formation. Even the distribution of dark matter may subtly respond to their presence. In this way, black holes are teachers. They demonstrate gravity's extremes. They expose the elasticity of time. They reveal how light and matter respond to curvature. Every orbit, every bent photon, every slowing second is a lesson in cosmic geometry. Yet, for all their power, black holes remain serene in their operation. No chaos erupts at a distance. No violent storms appear outside the event horizon. Their influence is gentle, steady, inexorable. A whisper of gravity, a pull of space-time, a soft bending of light. Even the dramatic events, collisions, mergers, jets follow natural patterns. They do not break the rules. They unfold according to precise mathematics. Each wave, each pulse, each arc of radiation is part of a cosmic rhythm. Slow, steady, peaceful, in its own profound way. When two black holes merge, they send ripples across the universe. Gravitational waves move like gentle waves on a vast cosmic ocean. These waves stretch and compress space-time minutely. They carry information about mass, spin, and orbit. They let us listen to events billions of years old. A quiet conversation across time and space. These events teach patience. They remind us that cosmic change often occurs slowly, measured over millions or billions of years. Yet, when observed carefully, the beauty and symmetry of these motions becomes apparent. Patterns emerge, curves align, space and time reveal their dance. As we reflect on this, we sense something profound. Black holes are extreme. They are mysterious, yet they are harmonious. They are not violent by nature. They are simply points where the laws of physics are most visible, where space curves most deeply, where time stretches most gently. The universe around them responds calmly. Stars orbit, light bends, matter accretes, time dilates, everything flows, as though the cosmos itself breathes slowly and peacefully. And in this soft, infinite stretching of space-time, we see a lesson. Even the most extreme phenomena can unfold with quiet elegance. Even darkness can guide light. Even gravity can nurture understanding. Black holes bend space and time, but in doing so, they reveal the universe in a slow, gentle, almost meditative way. As we drift further along the gentle curves of space-time, we encounter another fascinating feature of black holes. This is the phenomenon of tidal forces. A black hole's gravity is not uniform. It pulls differently on objects depending on distance. The difference in pull across a single body is called a tidal force. Near smaller black holes, these forces can become extreme, stretching an object along the direction of the pull, compressing it along other axes. Physicists sometimes call this effect spaghettification, a soft, dramatic term for a slow, inevitable stretching. But for supermassive black holes, the experience is more gentle. The tidal forces at the horizon may be almost negligible. You could cross the event horizon without ever noticing the stretch. No violent tearing, no sudden disruption, just a smooth continuation of your journey inward. This difference reveals an important lesson. Size matters. Gravity is relative. Extreme curvature can feel terrifying in theory, but mild in practice. It depends on scale, and it depends on perspective. Now, imagine a star venturing too close to a black hole. Its outer layers begin to stretch. Gas is pulled away. Streams of matter spiral into the black hole. These streams form a luminous accretion disk, hot, glowing, and beautifully structured, radiating energy across the electromagnetic spectrum. This process can last thousands of years. Slow, measured, a cosmic feeding in silence. And yet, it provides astronomers with information about both the black hole and the star. Mass, composition, spin, everything becomes a story written in light and motion. The energy released in this gentle feeding can power jets. Streams of plasma expelled at nearly the speed of light. They extend for thousands of light years. They shape galaxies. They heat interstellar gas. They create vast, glowing tendrils visible across the universe. Even in their apparent violence, black holes operate gracefully. Matter follows predictable paths. Energy moves along structured channels. Time flows along warped yet smooth trajectories. Space curves, but not chaotically. The universe bends around them, but never breaks. In this way, black holes are both destructive and creative. They consume, yes, but they also sculpt. They regulate. They shape the cosmos silently and steadily, without drama, without noise, without urgency. Their influence extends beyond visible matter. Even light from distant stars is affected. Paths bend, shadows form, multiple images appear. Gravitational lensing turns the universe into a subtle optical illusion. Stars duplicate, galaxies stretch. The cosmos becomes a living artwork shaped by gravity itself. Through these effects, we gain insight into the deep principles of physics. General relativity becomes tangible. Time dilation becomes observable. The bending of light becomes measurable. Gravitational waves whisper their story to sensitive instruments on Earth. Each observation builds a picture of the universe that is at once extreme and elegant. Chaos is tempered by structure. Violence is balanced by geometry. Destruction is accompanied by creation. And through all of it, the cosmos remains peaceful at its core. Even as matter falls inexorably inward, it moves along predictable paths. Even as light bends and stretches, it obeys the rules of spacetime. Even as time slows near the horizon, it does so smoothly. There is rhythm in the apparent chaos. There is pattern in the extremes. There is calm within the storm of gravity. Black holes, then, are not simply voids. They are laboratories, teachers, portals to understanding. They show us how space can curve, how time can stretch, how information might survive against all odds. And as we reflect on their silent, powerful presence, we feel a gentle awe, a calm reverence for the laws of physics, a soft wonder at the way the universe bends and shapes itself, at the elegant symmetry hidden within extreme phenomena, at the quiet lessons flowing from dark, silent giants. As we continue our gentle voyage through the warped geometry of the cosmos, another subtle effect of black holes comes into focus. This is the twisting of space-time itself. Known as frame dragging, it occurs when a black hole spins. The rotation of mass drags the surrounding space-time along with it. Imagine space as a soft, elastic fabric. A spinning black hole twists that fabric around itself. Objects nearby cannot remain completely stationary. They are carried along by the subtle rotation of space-time. Even light bends slightly, following the whirl. This twisting is not violent. It is a gentle, persistent influence. It subtly alters orbits. It shifts the paths of infalling matter. It changes the shape of the photon sphere. It creates a soft, cosmic eddy, spiraling slowly outward. Rotating black holes also reveal a region called the ergosphere. Outside the event horizon, space-time is dragged faster than the speed of light, relative to distant observers. Here, particles and light are forced to co-rotate with the black hole. Yet, energy can still escape. This creates opportunities for cosmic processes, like the Penrose process, where energy can be extracted from the rotation of a black hole. Through this gentle, persistent motion, the universe teaches us that nothing is ever truly still. Even in the deepest darkness, space-time flows. Even in the most extreme environments, physics remains consistent. Everything moves along predictable curves. Everything follows geometric patterns. The combination of mass, spin, and charge creates a rich tapestry of phenomena. Gravitational waves ripple outward from mergers. Accretion disks glow with high-energy radiation. Jets shoot across thousands of light years. Light bends, stretches, and duplicates. Time slows near the horizon. Space itself twists. Even the collapse of massive stars into black holes is a story of balance. A dying star contracts under its own gravity. Its core densifies. Electrons and protons combine. Neutrons dominate. Eventually, nothing halts the inward motion, and the event horizon forms. This transformation is both violent and silent, powerful and serene. The star disappears from view, yet the universe continues its rhythmic motion around it. Nearby stars respond. Orbits adjust. Matter flows. Light bends. Everything dances according to the geometry dictated by the new black hole. The cosmic order persists, guided by the subtle hand of gravity. Even hypothetical, black holes, primordial, tiny, or extremely massive, follow these rules. Their mass shapes space. Their spin twists it. Their presence bends time. Even in thought experiments, these principles hold true. They are universal. They are elegant. They are gentle in their extreme precision. As observers, we are invited to watch slowly, to measure carefully, to appreciate the curves, the flows, the bends, and the stretches. Every photon, every orbit, every second carries a lesson. The universe is revealing its design in whispers rather than shouts. And through all this, a sense of calm emerges. The black hole is not a monster. It is a sculptor. It shapes space and time silently. It bends reality softly. It teaches patience, precision, and awe. It reminds us that even in extreme conditions, the universe is harmonious. The study of these phenomena does not need to rush. Observing slowly, contemplating gently, and understanding quietly are enough. The cosmos rewards patience. Curiosity blooms in stillness. Knowledge deepens in quiet observation. Through this, black holes become guides rather than threats. They show how space can curve without breaking, how time can stretch without stopping, how information might endure even when hidden. They are silent mentors of physics, soft, patient, and profoundly wise. As we drift further into the quiet expanse near a black hole, we begin to notice another subtle effect. The gravitational lensing we discussed earlier not only bends light, but it also magnifies distant objects. Stars behind the black hole appear brighter. Galaxies are stretched into arcs and rings. Light travels along curved paths, revealing the hidden structure of the cosmos. This bending of light allows astronomers to study objects otherwise invisible. Faint stars and galaxies become observable. Cosmic structures are mapped. We see the universe as if through a gentle, natural magnifying glass. The black hole becomes both a shadow and a window, a dark lens that reveals the cosmos in soft, curved light. Meanwhile, matter falling into the black hole forms the accretion disk. Particles spiral inward in a smooth, predictable orbit. Friction and collisions heat the gas. X-rays and gamma rays are emitted. These signals travel vast distances, carrying information about the black hole's mass, spin, and orientation. The universe whispers its secrets through these high-energy photons. As the disk rotates, it can generate jets of plasma along the poles. These relativistic jets extend for thousands of light years. They push interstellar gas. They sculpt galactic environments. They influence star formation, spreading energy across cosmic distances. Even the extreme energy near a black hole follows patterns. There is structure, order, and symmetry. Nothing is random. Nothing is chaotic beyond recognition. Every orbit, every photon, every particle obeys the gentle curves of space-time. Now, consider time dilation again. If a spacecraft hovers near the event horizon, its clock ticks more slowly than a distant clock. Minutes for the observer inside may pass, while years flow outside. Time is personal, elastic, curved by gravity, and black holes stretch this effect to its extreme. Inside the ergosphere of a rotating black hole, frame-dragging twists both space and time. No object can remain at rest relative to distant stars. Everything is carried along the swirl of space-time. Even light itself rotates gently around the singularity. The universe is bending, stretching, and twisting in perfect mathematical harmony. All these effects combine to make black holes laboratories for understanding fundamental physics. They reveal how general relativity and quantum mechanics intersect. They challenge our understanding of information, matter, and energy. They show that space and time are flexible, malleable, and interconnected. They remind us that the universe has depth beyond the visible and measurable, and yet, despite the extreme curvature of space-time, the black hole is silent. It emits no sound. Its surface is invisible. Its interior unreachable. It operates calmly, obeying the rules of physics in complete stillness. This silence teaches us a lesson. Great forces do not require loudness. Power can exist quietly. Influence can be exerted gently. And the most profound phenomena may unfold in perfect serenity. As we step back in imagination, we see the black hole not as a monster, but as a master of geometry, a guide to the universe's deepest truths, a sculptor of space and time, a teacher in the language of curves, light, and seconds. And as we reflect on these lessons, a sense of calm spreads through the mind. The universe is extreme, yes, but it is harmonious. It is precise. It is gentle in its unfolding. Every photon, every orbit, every second is a note in a cosmic symphony. and black holes conduct it with silent grace. As we float further along the fabric of warped space-time, another subtle phenomenon appears. It is the bending of matter itself as it spirals toward the black hole. Gas, dust, and even whole stars follow curved paths dictated by gravity. The motion is slow, measured, predictable. Inside the accretion disk, friction generates heat. Particles collide softly. Energy radiates outward in gentle waves. X-rays, gamma rays, and visible light all escape, carrying information to distant observers. Through these faint signals, we can trace the mass, spin, and orientation of the black hole. The bending of space also affects time. Near the event horizon, time slows for those who venture close. Moments stretch, seconds dilate, minutes expand. From a distance, the infalling matter appears to freeze, frozen in place, suspended at the edge of the black hole. Yet, from the perspective of the matter itself, everything proceeds normally. Clocks tick at their usual pace. Particles move along their paths. Nothing seems unusual. Gravity guides gently. Space curves naturally. Time flows consistently within its own frame. The photon sphere is another striking feature. Light can orbit the black hole in a delicate, eternal circle. No escape, no fall, just endless, gentle motion. A ballet of photons tracing the curvature of space-time. Beyond the horizon, in the ergosphere of a spinning black hole, frame dragging twists, space and time together. Everything is carried along the swirl. Objects, light, and even the structure of space-time itself rotate. This rotation allows for subtle energy extraction. Matter can leave with more energy than it arrived with. The black hole's rotation is not destructive in this case, but transformative. Even gravitational waves, emitted during black hole mergers, carry this elegance. They ripple outward slowly, stretching and compressing space-time, whispering the story of mass, spin, and orbit across the universe. These waves are gentle signals of cosmic events billions of years old, traveling silently through the darkness. Black holes teach us about extremes in a calm way. They bend space. They stretch time. They twist light. They shape matter. And yet, they do so without chaos. Everything obeys predictable, elegant laws. Even the most extreme theoretical black holes, primordial, tiny, or supermassive, follow these principles. Size changes the intensity of tidal forces. Spin alters frame, dragging. Charge modifies the electromagnetic interactions. But the gentle bending of space and time remains. Harmony persists, even in extreme conditions. As we drift in imagination near these cosmic giants, a sense of peace emerges. The universe is extreme, but not violent. The darkness is vast, but not hostile. The curvature of space-time is profound, but smooth. Even in the presence of infinite density, physics remains consistent. Black holes, in their silent operation, offer lessons in patience and observation. Power can be quiet. Influence can be subtle. Understanding emerges from careful, gentle study. And as we slowly pull away, leaving the black hole behind in thought, we carry with us a soft sense of awe. The universe is extreme, beautiful, and harmonious. Its darkest regions teach us not fear, but wonder. They bend space, they bend time, and in doing so, they bend our imagination toward deeper understanding. As we continue our gentle drift near the curved space-time of a black hole, we encounter another quiet truth. Black holes are not isolated. They exist within galaxies. They interact with stars, gas, and dark matter. Their gravity sculpts the environment around them. Orbits adjust. Matter spirals. Light bends softly. Even supermassive black holes, millions or billions of times the mass of our sun, follow these gentle rules. Stars near the center of a galaxy move along predictable orbits. Gas clouds flow into accretion disks. Jets form along the poles, spreading energy across thousands of light years. The universe responds to their presence with balance and grace. Time near these giants is stretched. Seconds near the horizon feel longer than those far away. This dilation is subtle for distant stars, but extreme for anything approaching the horizon. Yet, within their own frame, all processes continue normally. Life, thought, and motion proceed undisturbed in their own pace. Even light is affected in mysterious ways. Paths curve along space-time. Photons circle the black hole, forming the photon sphere. Gravitational lensing magnifies distant stars. Rings of light appear. Arcs stretch across the cosmos. The universe reveals itself through curved, glowing patterns. The energy around black holes is also carefully structured. Accretion disks emit X-rays, gamma rays, and visible light. Jets of plasma travel outward at nearly the speed of light. Matter falls inward, following precise orbital paths. Even the most energetic processes obey the soft geometry of spacetime. Gravitational waves ripple outward from collisions and mergers. They carry information across billions of light years. They stretch and compress the fabric of the universe in gentle, predictable waves. These signals allow us to listen to cosmic events long past. The universe speaks softly, yet clearly, to those who listen. The extreme curvature near black holes also leads to tidal forces. Objects are stretched along the direction of gravity, compressed along other axes. Spaghettification occurs near smaller black holes, but near supermassive ones, the effect may be almost imperceptible. The universe adapts to scale, bending without breaking. Even rotating black holes twist space and time. The ergosphere carries everything along its spin. Energy can be extracted. Frame dragging shapes orbits. Space itself is in motion. Time flows differently depending on proximity. All these effects combine into a cosmic symphony. Black holes bend space. They bend time. They shape matter and light. They influence the universe quietly, consistently, and beautifully. And as we drift away from the horizon in our imagination, we carry a gentle understanding. The extremes of the cosmos can be calm. The darkest objects can teach. The bends and twists of space and time are soft when observed slowly. Patience and attention reveal the elegance of gravity. Light, and motion. Black holes, in their silent mastery, show us the universe as it truly is: structured, harmonious, patient, a vast, flowing expanse of curves and rhythms. Every photon, every particle, every second participates in this serene ballet. As we continue our slow journey through the quiet curves of space-time, we notice the subtle interaction between black holes and the surrounding universe. Black holes do not exist in isolation. They influence stars, gas clouds, and even dark matter. Their gravity shapes the orbits of nearby stars. It channels matter into accretion disks. It guides jets of plasma across thousands of light years. These jets carry energy outward. They sculpt galaxies. They regulate star formation. They create balance within the cosmic ecosystem. Even the most violent processes are structured, predictable, and elegant. The bending of light near a black hole creates fascinating visual effects. Gravitational lensing magnifies distant stars. Multiple images appear. Rings of light form around the black hole. Arcs stretch across the sky. The universe becomes a living, flowing artwork. Time, too, behaves differently near a black hole. It slows as one approaches the event horizon. Minutes stretch into hours. Seconds elongate softly. Yet, inside its own frame, time continues normally. Nothing feels out of pace. Nothing feels abrupt. Frame dragging adds another layer of subtle complexity. Rotating black holes twist space-time. Objects, light, and even the shape of orbits rotate gently along with the black hole. Energy can be extracted from this spin. Matter flows predictably along these curves. The universe obeys the geometry, moving with quiet grace. Even in mergers, black holes operate harmoniously. Gravitational waves ripple outward. They stretch and compress space. They carry information from billions of years ago. Observers can detect these whispers and learn about mass, spin, and orbit. Every ripple is a note in a cosmic symphony. Tidal forces near black holes can stretch objects into elongated forms. This spaghettification is dramatic in theory, but subtle in practice near supermassive black holes. The universe adapts to scale, bending without breaking. Space and time curve smoothly. Matter moves along gentle paths. The photon sphere encircles the black hole. Light can orbit endlessly. Glowing rings form as photons trace curved paths. Gravitational lensing enhances the effect. The universe glows softly in response. Even the most extreme black holes follow the laws of physics faithfully. Mass, spin, and charge determine the curvature of space. The bending of light and stretching of time proceed naturally. Chaos is absent. Harmony prevails. As we drift further away, leaving the event horizon behind in imagination, a sense of calm washes over us. The universe is extreme, yet gentle. Its darkness teaches wonder. Its curves reveal elegance. Its slow processes show patience. Black holes, in their quiet majesty, demonstrate the profound beauty of the cosmos. Space bends. Time stretches. Light curves. Matter flows. And through all this, a gentle, meditative harmony persists. As we drift even farther from the immediate influence of the black hole, we begin to see its subtle effects on the larger cosmos. Galaxies rotate and bend under its gravity. Clusters respond to its pull. Even dark matter may subtly align along the paths dictated by these invisible giants. The bending of light, the stretching of time, and the twisting of space all combine into a magnificent cosmic ballet. Every photon, every particle, every ripple of energy follows the gentle curves of space-time. Patterns emerge from the darkness. Harmony arises from what seems extreme. Black holes continue to teach us about the universe's extremes without rushing. Their processes unfold over millions, sometimes billions of years. Yet every effect is observable with patience. Every interaction reveals a deeper law. Every motion demonstrates a principle of physics. Even the accretion of matter, the spiraling of stars, and the emission of jets follow predictable paths. Time slows for those near the horizon, yet continues normally within. Light bends into rings and arcs. Gravitational waves ripple across vast distances. The universe communicates gently, silently, yet clearly. The rotation of a black hole twists space-time itself. Frame dragging guides the motion of nearby objects. Energy can be extracted from this rotation. The universe flows in perfect geometric order. Even extreme phenomena remain harmonious. Tidal forces stretch and compress matter. Spaghettification occurs near smaller black holes. Near supermassive ones, the effect is almost imperceptible. Scale determines perception. Gravity bends, but does not break. Photon spheres encircle these giants. Light can orbit endlessly, trapped in a delicate, eternal dance. Rings of glowing photons form, capturing the imagination of all who study them. Gravitational lensing magnifies the distant universe, revealing hidden stars and galaxies. Through mergers and collisions, black holes generate gravitational waves. These waves stretch and compress space-time gently. They carry messages from billions of years ago. Observers on Earth can detect these whispers. Every wave, every ripple is a note in a universal symphony. And in all of this, time and space reveal their elasticity. Seconds slow near the horizon. Minutes dilate. Light bends. Matter moves along precise orbits. The universe operates with exquisite patience. Black holes are not merely objects of destruction. They are sculptors of the cosmos. They shape, they guide, they inform. They create harmony through curvature. They bend space. They bend time. They bend our imagination gently toward understanding. Even in darkness, the universe is luminous. Even in extremes, there is elegance. Every orbit, every photon, every second flows according to natural laws. Every motion is part of a quiet cosmic rhythm. And as we slowly drift away from the black hole in our mind, a sense of peace remains. We carry with us the lessons of bending space, stretching time, and curving light. We understand the silent mastery of these cosmic giants. We feel the calm, patient rhythm of the universe itself. And in this quiet, meditative space, we are reminded that even the most extreme corners of reality are harmonious, ordered, and breathtakingly beautiful. The black hole teaches us that in the vastness of the cosmos, even darkness has structure. Even silence carries information. Even gravity can nurture understanding. Through its bends, stretches, and twists, the universe speaks softly. And if we listen carefully, we drift gently along with it, calm, awed, and at peace. As we continue our serene journey through the cosmos, let us imagine drifting near a black hole in a small spacecraft. The vast emptiness stretches all around us. Stars glimmer softly in the distance. Space feels both immense and intimate. Every photon carries the memory of light years traveled. The gravitational pull of the black hole is strong, yet we float peacefully, guided by careful navigation. Matter nearby forms a luminous accretion disk, glowing softly in shades of gold, orange, and deep red. Gas spirals inward in smooth paths. Every orbit is precise. Every particle follows the gentle curves of spacetime. Time near the black hole moves differently from far away. Clocks on the spacecraft tick slowly compared to those on distant planets. Moments expand. Seconds stretch gently. Yet, within the spacecraft, time feels normal. Life continues, calmly, without disruption. The twisting of spacetime, due to the black hole's rotation, is subtle but measurable. Objects are carried along by frame, dragging. Even light follows a gentle spiral. Energy can be extracted from this motion. The universe seems to dance quietly, following the rules of physics with patient elegance. Gravitational lensing bends light from distant stars. Rings form around the black hole, glowing softly in the darkness. Multiple images appear. The cosmos becomes a delicate kaleidoscope of curved light and shadow. Every curve, every bend tells a story of geometry, mass, and energy. Nearby stars orbit with measured grace. Their paths, though altered by the black hole's presence, remain stable and predictable. The galaxy itself seems to respond to the invisible pull. Gas clouds swirl. New stars form. Others drift into calm orbits. Everything unfolds according to natural laws. Even extreme events, such as the collision of black holes, are rhythmic in nature. Gravitational waves ripple outward slowly, stretching and compressing spacetime. They carry messages across billions of light years. Observers on distant planets could detect these whispers if their instruments were sensitive enough. The universe communicates in soft, subtle pulses. We notice the tidal forces stretching matter. A star venturing too close to the horizon elongates gradually. Spaghettification is present, but not sudden. The process is slow, unfolding over long periods. Scale and distance dictate the gentleness of these phenomena. As we drift further, light itself forms intricate patterns around the black hole. Photons orbit in the photon sphere, tracing endless loops. Rings of glowing light shimmer faintly. Even in darkness, the universe glows softly. Gravitational lensing enhances distant stars, revealing structures hidden from ordinary view. Supermassive black holes exert subtle influence on their galactic neighborhoods. Jets of plasma emerge along the poles. They distribute energy across thousands of light years. They regulate star formation. They maintain equilibrium within the galaxy. All this occurs silently, with cosmic patience. Black holes demonstrate a unique blend of extremes and serenity. They bend space. They stretch time. They influence matter and light. Yet their operations are predictable, harmonious, and calm. Even in their most powerful actions, the universe remains structured and gentle. Observing these effects invites contemplation. Patience allows us to perceive subtle curvatures of space. Careful attention reveals the stretching of time. A slow journey near a black hole becomes a meditation on the laws of the universe. We witness order emerging from what initially seems chaotic. In this quiet observation, the black hole becomes a teacher. It shows the flexibility of spacetime. It demonstrates the persistence of natural law. It whispers lessons about energy, gravity, and the flow of time. Its silent presence is profound, majestic, and calming. As we drift even farther away from immediate influence, we perceive the bending of the galaxy itself. Stars adjust orbits over millennia. Gas flows in elongated patterns. Light curves around invisible centers. The universe operates like a soft, infinite symphony, guided by the gentle hand of gravity. Even hypothetical events, like the creation of miniature black holes or the influence of dark matter, follow these gentle rules. Extreme mass, rapid spin, or concentrated charge all alter the intensity of local effects. But harmony persists. Space bends without breaking. Time stretches without stopping. Energy flows according to geometric precision. Black holes teach patience. They reveal that even in extremes, the universe is orderly. They encourage observation, reflection, and calm. We see that destruction is balanced by creation. Darkness is paired with illumination. Gravity bends the cosmos into soft, flowing arcs. And as we slowly pull away, leaving the black hole in imagination, a sense of serenity pervades. The universe is vast. It is extreme. Yet, it is harmonious. Every orbit, every photon, every wave is part of a slow, meditative rhythm. We carry with us the lesson, even in darkness. There is calm. As we continue drifting through the vastness near a black hole, the universe feels expansive yet intimate. Light from distant stars stretches gently as it curves around the invisible mass. Every photon traces a path dictated by the geometry of spacetime. The black hole's presence is subtle, yet profound. Accretion disks rotate slowly, glowing with a soft, golden hue. Matter spirals inward, following curved paths with elegant precision. Friction generates warmth. Particles collide in predictable ways. Energy radiates outward. X-rays, gamma rays, and visible light illuminate the darkness softly. Time near the event horizon flows differently. Seconds stretch. Minutes elongate. Yet inside a moving frame, time appears normal. Processes unfold gently. No sudden shifts. No abrupt changes. Only the smooth rhythm of gravitational influence. Nearby stars orbit with quiet elegance, their paths adjust gradually, creating a subtle dance around the black hole. Even stellar systems respond with precision. Everything aligns according to the invisible curves of space and time. The cosmos moves slowly, methodically, with calm patience. Gravitational lensing creates breathtaking visuals. Stars duplicate. Galaxies stretch. Rings of light form around the black hole. Soft and luminous, these arcs magnify distant objects, revealing structures previously hidden from view. The universe becomes a living mosaic of light and curvature. Frame dragging adds another layer of subtle beauty. Rotating black holes twist the surrounding spacetime. Objects and light are carried gently along with the spin. Energy can be extracted from this rotation. Everything flows according to the mathematical elegance of the cosmos. Tidal forces stretch matter along the pull of gravity. Stars venturing too close elongate gradually. Spaghettification is slow and deliberate near supermassive black holes. Scale and distance determine the intensity of these effects. Even the most extreme forces proceed with cosmic grace. Jets of plasma emerge along the black hole's poles. They extend thousands of light years. They distribute energy. They influence star formation. They sculpt galactic structures. All of this occurs without chaos. Order prevails. Harmony is maintained. Gravitational waves ripple outward from mergers, collisions, and disturbances. They stretch and compress space-time, carrying messages across billions of light years. Observers, patient and attentive, can detect these whispers of the universe. Every wave is a note in the slow, melodic symphony of cosmic events. Even the photon sphere around a black hole exhibits silent beauty. Light orbits endlessly in delicate loops. Rings glow faintly. Every photon is a dancer following the curves of spacetime. The universe reveals itself through soft, luminous patterns. The influence of a supermassive black hole extends across its galactic neighborhood. Stars adjust orbits over millennia. Gas clouds spiral along gentle paths. Light bends, creating arcs and distortions. The galaxy responds quietly, yet with profound structure. Extreme events, like black hole mergers or the creation of a binary system, unfold slowly on cosmic timescales. Gravitational waves ripple outward. Matter and energy move predictably. The universe communicates through these slow, subtle motions. We are invited to observe, patiently, in awe and calm. Even hypothetical black holes, primordial or tiny, demonstrate these principles. Extreme mass, rapid spin, or charge influences local effects. But space bends gently. Time stretches smoothly. The universe remains in equilibrium. Observing these phenomena encourages quiet reflection. Patience allows us to notice subtle curves. Careful attention reveals slow stretching of time. Light bending becomes mesmerizing. The cosmic rhythm unfolds, gentle and continuous. Black holes teach lessons in patience, precision, and observation. They reveal the flexibility of space-time. They demonstrate that even extremes can be harmonious. They show that gravity, though powerful, can operate with gentle consistency. As we drift farther in imagination, leaving the black hole behind, a sense of serenity grows. The universe is vast, extreme, yet ordered. Every orbit, every photon, every wave participates in a meditative rhythm. Even in darkness, the cosmos glows softly. Even in extremes, harmony persists. And so, we carry forward the quiet lessons of the black hole, the bending of space, the stretching of time, the curving of light, a gentle understanding of the universe's profound yet calming design. As we float further into the quiet vastness around a black hole, we notice how space itself seems soft and pliable. Light curves gently along invisible paths. Stars twinkle in subtle arcs. Galaxies stretch in luminous patterns, guided by gravity. The universe feels both infinite and intimate. The accretion disk rotates slowly, glowing with a soft, golden, and red light. Gas spirals inward, following the gentle curvature of space-time. Friction warms particles. Energy radiates outward in a calm spectrum of X-rays, gamma rays, and visible light. Every photon traces a predictable path. Every orbit is part of a quiet, cosmic rhythm. Time near the event horizon flows differently than far away. Seconds stretch softly. Minutes elongate. Yet, inside our imagined frame, time feels normal. Processes unfold gently. Nothing is rushed. Nothing abrupt occurs. Nearby stars respond to the black hole's presence with graceful orbits. Even stellar systems adjust over centuries. Matter drifts along precise curves. The galaxy itself seems to bend slightly in response. Energy flows quietly along predetermined paths. Order persists even amidst extremes. Gravitational lensing enhances distant stars. Rings of light form around the black hole. Arcs stretch softly across space. These effects magnify distant galaxies. Hidden cosmic structures become visible. The universe reveals its geometry with subtle elegance. Rotating black holes twist spacetime gently. Frame dragging carries objects and light along soft spirals. Energy can be extracted through these motions. The universe flows smoothly, following the elegant rules of geometry. Even extreme gravity operates with calm consistency. Tidal forces stretch and compress matter. Stars venturing near the horizon elongate gradually. Spaghettification unfolds slowly, almost imperceptibly, near supermassive black holes. Scale determines the intensity. Gravity bends without tearing. Time stretches without abrupt halts. Jets of plasma emerge from the poles of the black hole. They extend thousands of light years into the galaxy. They distribute energy gently. They regulate star formation. They shape galactic structures quietly. Harmony remains, even in these extreme processes. Gravitational waves ripple outward from collisions or binary mergers. They stretch and compress spacetime over vast distances. Observers patient enough can detect these whispers. Every wave carries information about mass, spin, and orbit. The universe communicates softly, persistently, with quiet elegance. Even the photon sphere displays subtle beauty. Light orbits endlessly, Rings glow faintly against the darkness. Every photon follows a precise, graceful path. The universe reveals its patterns through these delicate luminous loops. Supermassive black holes influence entire galactic neighborhoods. Stars adjust orbits over millennia. Gas clouds spiral along gentle curves. Light bends in arcs and rings, magnifying cosmic structures. The galaxy dances to the quiet tune of gravity. Extreme events, like mergers, unfold over millions of years. Gravitational waves ripple outward. Matter and energy move predictably. The universe communicates slowly, inviting careful observation. We are guided to witness its elegance with patience and calm. Even hypothetical black holes, primordial or tiny, follow these principles. Mass, spin, and charge determine local effects. Yet, space-time bends smoothly. Time stretches gently. Energy flows according to precise geometric rules. Observing these processes teaches patience. It encourages quiet reflection. Careful attention reveals slow curvature of space, stretching of time, and bending of light. The universe operates like a vast, meditative rhythm. Even in extremes, calm persists. Black holes serve as teachers. They reveal flexibility and precision in the universe. They show that even extreme forces can operate harmoniously. They remind us that gravity, though immense, can be gentle. As we drift farther in imagination, leaving the black hole behind, serenity fills the mind. The universe is vast, extreme, yet ordered. Every photon, every orbit, every ripple participates in a slow, meditative, cosmic rhythm. Even in darkness, light glows softly. Even in extremes, the universe remains harmonious. And so, we carry with us the quiet lesson of the black hole. Space bends, time stretches, light curves. The cosmos is vast, intricate, and profoundly serene. Every motion, every wave, every orbit flows in gentle harmony. As we drift slowly through the calm reaches near a black hole, we notice the universe bending ever so gently around its mass. Light curves along invisible paths. Stars twinkle in arcs and rings. The black hole's presence is profound, yet quietly orchestrated. Even extreme gravity unfolds with elegance and patience. The accretion disk glows softly, rotating in smooth spirals. Gas flows inward, guided by the gentle curvature of space-time. Friction warms particles. Energy radiates outward, a calm spectrum of X-rays, gamma rays, and visible light. Every photon travels along a predictable path. Every particle follows the quiet curves of the cosmos. Time, near the event horizon, stretches slowly. Seconds elongate. Minutes drift gently. Yet, within the spacecraft or frame moving nearby, time feels normal. Nothing is rushed. Processes unfold gradually, softly, with cosmic rhythm. Stars nearby adjust orbits with calm precision. Even entire stellar systems respond slowly to the black hole's influence. Gas clouds spiral along gentle trajectories. Light bends. Galaxies shift imperceptibly. Everything aligns according to the natural laws of space-time. Gravitational lensing reveals hidden structures. Rings of light form. Distant galaxies are magnified. Arcs stretch across the sky, soft and luminous. The universe unveils its geometry in subtle, intricate patterns. Frame dragging twists space-time around a rotating black hole. Objects and light are carried along in gentle spirals. Energy can be extracted from this rotation, a soft, powerful phenomenon. The cosmos flows with elegance, every motion precise and harmonious. Tidal forces stretch matter slowly. Stars venturing too close elongate gradually. Spaghettification unfolds almost imperceptibly near supermassive black holes. Scale dictates the gentleness of these effects. Gravity bends without tearing. Time stretches without abrupt stops. Jets of plasma flow from the poles of the black hole. They reach thousands of light years. They distribute energy, regulating star formation. They shape galactic structures. Even in extreme processes, harmony prevails. Gravitational waves ripple outward from mergers. They stretch and compress space-time across vast distances. Every wave carries information about mass, spin, and orbital dynamics. Observers, patient enough, can detect these whispers of the universe. Every wave is a note in the slow, melodic symphony of cosmic events. The photon sphere encircles the black hole. Light orbits endlessly. Glowing rings shimmer softly. Every photon dances along the gentle curves of space-time. Even in darkness, the universe emits a faint glow. Supermassive black holes influence entire galaxies. Stars adjust orbits over millennia. Gas flows in curved paths. Light bends softly. The galaxy responds quietly, orchestrated by the invisible hand of gravity. Extreme events unfold slowly on cosmic timescales. Collisions, mergers, and binary formations ripple gently through space. Gravitational waves propagate, stretching and compressing space-time. Matter and energy follow predictable paths. The universe communicates with calm elegance. Even hypothetical black holes, primordial or tiny, adhere to these principles. Mass, spin, and charge determine the intensity of local effects. But space-time bends smoothly. Time stretches gently. Energy flows along precise curves. Harmony remains. Observing these phenomena encourages quiet reflection. Patience allows perception of subtle space-time curves. Careful attention reveals time dilation. Light bending becomes mesmerizing. The cosmic rhythm unfolds, gentle and continuous. Black holes are teachers in silence. They demonstrate precision and flexibility. They show that even extremes can be harmonious. Gravity, though immense, operates with gentle consistency. As we drift away, leaving the black hole behind in imagination, serenity fills the mind. The universe is vast, extreme, yet ordered. Every photon, every orbit, every ripple flows in a meditative rhythm. Even darkness glows softly. Even extremes remain harmonious. And so, we carry forward the quiet lessons of the black hole. Space bends. Time stretches. Light curves. The cosmos is vast, intricate, and profoundly serene. Every motion, every wave, every orbit flows in gentle harmony. As we drift gently through the vast, quiet expanse around a black hole, the universe reveals its subtle beauty. Light bends softly along the curves of space-time. Stars twinkle in arcs. Galaxies stretch in gentle patterns. Every motion feels measured, harmonious, and precise. The accretion disk glows with a soft golden light. Gas spirals inward in smooth, predictable paths. Friction warms particles. Energy radiates outward in X-rays, gamma rays, and visible light. Every photon follows the gentle curvature of space. Every particle dances in accordance with the laws of gravity. Time near the event horizon flows differently. Seconds stretch. Minutes drift slowly. Yet, within our imagined frame, time feels normal. Nothing is rushed. Processes unfold gently, in perfect rhythm. Stars nearby orbit gracefully. Stellar systems adjust over centuries. Gas clouds spiral along gentle trajectories. Light bends and curves. Galaxies respond quietly to the invisible force of gravity. Harmony persists amidst extremes. Gravitational lensing magnifies distant cosmic structures. Rings of light form around the black hole. Arcs stretch across the sky, soft and luminous. Hidden galaxies and stars become visible. The universe unveils itself with subtle elegance. Rotating black holes twist space-time. Frame dragging carries objects and light along gentle spirals. Energy can be extracted from this rotation. The cosmos flows with precise elegance. Even extreme gravity operates calmly and predictably. Tidal forces stretch matter slowly. Stars venturing too close elongate gently. Spaghettification unfolds gradually near supermassive black holes. Scale and distance determine the gentleness of these effects. Gravity bends without breaking. Time stretches without abrupt halts. Jets of plasma flow outward from the black hole's poles. They extend thousands of light years. Energy is distributed gently. Star formation is influenced softly. Galactic structures take shape, orchestrated by these silent forces. Gravitational waves ripple outward from collisions and mergers. They stretch and compress space-time across vast distances. Every wave carries information about mass, spin, and orbit. Observers patient enough can detect these whispers. Every wave is a note in the cosmic symphony. The photon sphere encircles the black hole. Light orbits endlessly. Glowing rings shimmer softly. Every photon follows a precise, elegant path. Even in darkness, the universe emits a gentle glow. Supermassive black holes influence entire galaxies. Stars adjust orbits over millennia. Gas clouds spiral along curved paths. Light bends softly. The galaxy moves to the quiet rhythm of gravity. Extreme events, like mergers or the formation of binaries, unfold slowly. Gravitational waves ripple outward. Matter and energy follow predictable trajectories. The universe communicates with calm elegance, inviting quiet observation. Even hypothetical black holes, primordial or tiny, follow these principles. Mass, spin, and charge influence local effects. Yet space bends smoothly. Time stretches gently. Energy flows along precise curves. Harmony is preserved. Observing these phenomena encourages reflection. Patience allows perception of subtle curves. Careful attention reveals time dilation. Light bending becomes mesmerizing. The cosmic rhythm unfolds slowly, continuously, and gently. Black holes are silent teachers. They demonstrate precision and flexibility. They show that extremes can coexist with harmony. Gravity, though immense, operates with quiet consistency. As we drift farther from the black hole in imagination, serenity fills the mind. The universe is vast, extreme, yet ordered. Every photon, every orbit, every wave participates in a meditative rhythm. Even darkness glows softly. Even extremes remain harmonious. And so, we carry forward the quiet lessons of black holes. Space bends, time stretches, light curves. The cosmos is vast, intricate, and profoundly serene. Every motion, every wave, every orbit flows in gentle, harmonious rhythm. Thank you for drifting with me through the quiet mysteries of how black holes bend space and time. As we leave the curved edges of space-time behind, may the calm of the cosmos stay with you soft, steady, and peaceful. If your mind feels lighter, slower, or just a little more at ease, then the journey has done its work. Whenever you need rest, comfort, or a gentle voyage through the universe, the Sleep Scientist channel will be here to guide you. Wishing you a deep, quiet, and restorative sleep. Good night, and let the stars watch over you.